All right, section 9.4. We are going to keep this idea of a right triangle, but we're going to actually talk about some special right triangles that are out there. And again, just a reminder, guys, this whole chapter is all focusing on right triangles. And so far, we've really only like surface stuff. I mean, we've talked about Pythagorean theorem and the converse of it, which are both concepts that I think that you're comfortable with already.
Yeah.
This is kind of really starting the rest of the kind of the new stuff. Doesn't necessarily mean difficult, but things that are new that we
haven't seen before,
which not always what we think about right away. So keep this in mind with the new stuff that we might have to work a little bit harder to understand it. Okay? Now, what we're going to do on this section is we're going to start by just exploring a couple new theorems, okay, which essentially is dealing with a special right triangle, and there's two of them. So what we'd like you to do before we actually do this whole slide together is we'd like you to go ahead and do this part first. What I mean by that is find the missing side length in each of these triangles. So do that first and then check with us.
Okay.
So how did you go about finding the side lengths?
I used the Pythagorean theorem.
And the reason why we can do that is because they have
a right angle, and I have two missing sides, finding a third unknown.
Okay, so hopefully you've done that. Let's just check to see what you're getting for each of those missing sides.
All right, and we're not going to show our work, but I got a radical 2, and here I got a 3 radical 2 when I simplified it, and there was a side length of 6.
And I like that you said when you simplified it. We're not wanting any rounded answers here, okay? All right, so these questions kind of go along with these triangles, so I'm hoping you're going to think about this first and then check with us. Okay, so first question. How would you describe the triangles above?
Well, I noticed that they are all isosceles because they have two congruent sides, and they're all right triangles.
Good.
So isosceles right triangles.
And that's based on what we know. We know that those two legs are congruent in each of these. We know that they are obviously right triangles, so isosceles right. That's good vocab. All right, says, what are the angle measures in each of the triangles?
Well, I know that I've got one that's 90 degrees.
Okay.
And because it's isosceles, I know the base angles are congruent. So I know that each of those would have to be 45 in order to make up the rest of the 90.
So we have a 90 and then we have two 45-degree angles in each of those triangles. All right. Now the next question says, what relationship do you know? So I'm going to kind of direct this a little differently, okay, instead of just giving it broad. What do you notice about the sides?
Okay. So far we've really talked about the angles, yeah, and we know it's isosceles. Well, okay, I knew that the two legs obviously were congruent, but then I know that the hypotenuse, the longer side across from the right angle, seemed to be radical 2 times whatever the legs were.
So in this one, the leg was 1. If I take 1 times radical 2, do I get radical 2?
I do.
And then here, the leg is 3. Take that times radical 2, I got 3 radical 2. Same here. So it would be fair to say, and you said the hypotenuse was basically your leg times radical 2.
Right. Perfect.
Now, the cool thing is this is actually a theorem. And it's a nice and short and sweet theorem. It's called the 45-45-90 triangle theorem because of the fact that you're going to have a right angle for sure, and the two angles here are going to be 45. We could also call this isosceles right triangle. Okay, so I'm going to make a little note that this is also an isosceles right triangle. All right, now what are they saying? They're saying that the hypotenuse in this triangle is radical 2 times as long as each leg. And we know that each leg is basically the same length, or it is the same length. So this is a leg, and this is the hypotenuse. So if the leg was, let's say, x, both of them are going to be x, what's the hypotenuse going to be?
It would be x radical 2.
Yeah. So this is the relationship that this theorem is telling you, okay? The leg times radical 2 is going to get you the hypotenuse. So what's kind of convenient about this? Well, knowing that, would we need to go back and use the Pythagorean theorem every single time?
No, and actually I don't have to do any work at all.
That's like really convenient. Very convenient. Now, what if you forget? Well, that's there for you as well.
Yeah.
So that's why, guys, we know you're comfortable with this, and I think we sometimes gravitate to what we're comfortable with. but sometimes knowing something new will make things a little bit easier.
Yeah.
Right? So kind of keep that in mind. All right, help us explore the next one.
All right, now we're going to talk about the other type of special right triangle. And it's a 30, 60, 90 triangle. So thinking about that, we know the 90 tells us there's a 90-degree angle and a 30-degree angle and a 60-degree angle.
Okay, so this is one that you're in the last one we kind of were able to figure it out.
This one I'm going to give that to you.
Okay.
Now, I'm telling you that there's 2 legs and a hypotenuse, but it's not isosceles, so they're going to be 2 different lengths.
Okay.
So we're going to call one the shorter leg and one the longer leg, and then our hypotenuse. And I'm going to give you the shorter leg and the hypotenuse each time. And you're going to help me just find the longer leg. And I'll tell you what, guys, try this on your own first using the Pythagorean theorem and see if you see anything cool.
And reminder that the hypotenuse is your C. So remember to put that in for the C.
Okay, so Mrs. Palermo, we're not going to show our work here because we're going to assume that they can do the Pythagorean theorem. But what did you get for the longer leg for the first scenario?
I got radical 3.
And then for the second one?
2 radical 3 and 5 radical 3.
Love it. Now, what do you notice about some relationships just in general
of the sides? Okay, well, I'm looking at them, and the first thing that I'm going to notice based on kind of what you were saying with the shorter leg and the hypotenuse given, I've noticed the shorter leg doubled basically gets you the hypotenuse.
Yeah, and I gave you that, so that's not something I expected you to explore by finding the, using the Pythagorean theorem, but it's definitely true.
Okay.
So the hypotenuse
is basically 2 times the shorter leg.
2 times shorter leg. Love it. Okay, and then what else do you see?
I'm noticing something about the longer leg, and I'm noticing the longer leg is taking the shorter leg times radical 3.
Yeah. So to get the longer leg, we're going to take
the shorter leg times radical 3.
Yeah, I'll write it that way too.
Because usually you put the radical 3 on the ends.
All right, so just in general, if I said that the shorter leg was X, so I'm going to come up with my new scenario. Okay, let's talk about the hypotenuse first. You said it was going to be what?
2 times that, so it would be 2x.
And what about the longer leg?
It'd be x times radical 3.
Love it. And guess what? This is another theorem.
Yay!
So these are our 2 special right triangles. What's really nice about these is there's either very little work, which we'll see kind of some scenarios where you'll see why sometimes we'll need a little bit of work, or otherwise no work at all to show. So this is in a 30, 60, 90 triangle. It says the hypotenuse is twice as long as the shorter leg, and the longer leg is radical 3 times as long as the shorter leg.
Okay, so one of the first things I'm thinking, and I know that some of you are thinking as well, is I know where the hypotenuse is located.
Okay, where is the hypotenuse
Across from the right angle. So that's the hypotenuse. But, you say shorter leg and longer leg, and yeah, I can tell by looking at the picture how it looks shorter or looks longer. But is there a way to really know which one's the shorter leg and the longer leg?
Definitely. Last chapter we talked about some inequalities within a triangle. And so just thinking for a minute about some inequalities within a triangle, we know that when we are looking at the angle measures, we've got a smaller angle and a little bit larger, not the largest, but a little bit larger angle. And we know that when we compare those angles, what do you know about the side that's across from the shortest angle?
It'd be the shorter side, so that's the shorter leg. And then the one across from the 60-degree angle is the longer leg. Now, just be careful. Don't say it's the longer side because the hypotenuse technically is.
Exactly.
It's just the longer between the 2 legs. So always the longer leg is across from the 60 and the longer or shorter leg is always across from the 30.
Exactly. All right. So using that vocabulary and making sure we can identify where those are, they're saying everything is in terms of what?
The shorter leg.
So I'm going to say the shorter leg is X.
Okay.
What do we know about the hypotenuse compared to the shorter leg?
It's twice that, so 2 times x.
And the longer leg will be?
X radical 3.
Yeah. And that's going to happen every single time. So if I give you the shorter leg, no work whatsoever. All right. We're going to explore some problems where we can find those missing sides.
So first and foremost, guys, don't assume that you're going to have a special right triangle, but don't forget about them. So what I mean by that is now that we have this special right triangles, a lot of times that's the first thing I ask. Because if it is one, I know that the work involved is so much more convenient.
Oh, yeah.
Okay, if you immediately just gravitate to the Pythagorean theorem, that's not always a good option. And you're going to learn, as we progress in this chapter, the Pythagorean theorem is not going to be our go-to every single time.
Oh, no. In fact, very rarely.
Right now it is, or has been, but we're going to be adding so much more to our plate, okay? So, first things first, is this a special right triangle?
Yes.
Okay, and what kind is it?
It is a 45, 45, 90, and I know that because I've got the 90-degree angle marked, the perpendicular up there, and I've also got 145, so that leaves us obviously with the other one to be 45.
Okay, so if we have a 45, 45, 90 triangle, the first thing I ask after that is, what piece am I giving you, or which side are they giving you?
They're giving us one of the legs.
Ah, that's convenient. So we know legs are congruent in a 45, 45, 90, so these are both going to be 8. And what would the hypotenuse be?
8 radical 2.
So you found the missing sides.
That required no work whatsoever. I love this stuff.
Sweet. All right.
All right, so this next one, is this a special right triangle?
Well, it's isosceles right, which means it's a 45, 45, 90 triangle, which means yes, it is.
All right. And I love that you first noticed it was isosceles. It was an isosceles right triangle. Okay. Now, what piece did I give you here, though?
They're giving you the hypotenuse this time.
Yeah, we're given the hypotenuse. Usually if we're given the leg and we say, what do you know about the leg, and to be able to get to the hypotenuse, right? This time we're not starting with the leg.
So we're trying to find the leg. So let's label the legs X. Let's just call them X.
Sounds good.
Because they're going to both be the same. I know to get from the leg to the hypotenuse, basically I'm multiplying by radical 2. So if I do x radical 2, that's going to get you the hypotenuse of 12. All right. So it's just solving that equation. So I would just maybe divide each side by radical 2. And I end up with x equal 12 divided by radical 2.
And we're not going to leave it like that because that is not a rationalized denominator.
No, we're not going to type it in our calculator. No. We're going to rationalize it. So multiply the top and bottom by both radical 2. And I end up with 12 radical 2 over 2, which simplifies to 6 radical 2.
Love it.
So that's the lengths of the legs.
Guys, make sure that all of your answers from this point forward are those simplified radicals. The only time we're going to give some decimal answers is really when we're looking at maybe a specific type of units. But otherwise, we're going to be giving, if possible, if it's a radical, giving those simplified radicals.
And just to kind of piggyback on what she's kind of some of the things she's saying is, and also guys, you know, you think about checking it, you can also do, you put them in, does it actually equal c squared plus equal, or c squared equals a squared plus b squared? So actually substitute this in for the a and the b, and then the 12 in for c. Does it actually work? All right, so keep that in mind. All right, what's happening here? What do you see here? This looks a little different.
Yeah, I don't just see a triangle. In fact, I see two triangles that together seem to make up a square.
This is a square, but what is formed with these two triangles, or this square by the diagonal, is two
right triangles.
Right triangles, and even better, they are
isosceles right triangles. So we have special right triangles.
This is a special right triangle. So this is still a 45, 45, 90 triangle here. All right. Now, just to kind of keep in mind, just because it's isosceles doesn't mean it's going to be a 45, 45, 90 triangle. Or just because it's a right triangle doesn't mean it's going to be a special right triangle. So we do have to make sure we're for sure confident that this is a special type. And it is. Now, in this, they do give you the diagonal of the square, but the diagonal actually ends up being what of that?
Oh, it's the hypotenuse. This is like the last one where I have to work backwards.
So how do I get from the hypotenuse to a leg?
We had to divide by radical 2.
So if I divide by radical 2, I'm going to have to rationalize it. So radical 2 over radical 2. So I end up with 15 radical 2 over 2. All right. Can we simplify any further?
Not really.
No, because 2 doesn't go into 15. No. You can't divide 2 into radical 2. So what does that mean?
That's just my leg.
That's your leg. And that's actually the side.
That's all the sides.
All 4 of the sides, because they're all the same.
Okay.
Easy enough.
Sounds great. Okay, next one. This one says find the perimeter. which we'll get there in a minute.
Okay.
But let's first just ask ourselves the same question. Is this a special right triangle?
It is.
Okay. And what kind of a special right triangle is it?
It's a 30, 60, 90.
Because they give you the 30 and the 60. Obviously, it's a triangle, so what's left has to be the 90. Okay. Now, what piece of the 30, 60, 90 triangle do they give us?
Well, they're giving us the shorter leg. And I'm thinking, like, if they're asking to find the perimeter, we're going to have to find all three sides, right?
You're going to have to.
So if they give you only one, I got to find the other two. And since they give us the shorter leg, that's kind of convenient because the hypotenuse, which is across from the right angle, is twice that. So I'll do 2 times the 4. So that gives you 8. So that's the hypotenuse.
That doesn't look like 2 times 4. I'm just going to get rid of that. You guys, okay, 2 times 4.
So that's the hypotenuse.
Yes.
And to get the longer leg, I'm going to take the shorter leg times radical 3, so 4 radical 3.
Love it. And guys, if you forget when to use the radical 3 or when to use the radical 2, just something that I've said to my kids in the past that kind of seems to help them. When you've got 3 different side lengths or 3 different angle measures, that's when you've got the radical 3 piece attached to it. With the isosceles, the nice thing is they both have, you have 2 legs that are congruent, so you're going to have a radical 2 piece with that. So just to keep track, because I know sometimes we'll remember some of the relationships, but we forget which radical to use. So just something to kind of keep in mind. All right, now we're not done there.
No, we're not. And I think some people want to just stop. But we said find the perimeter.
So we need to add all the sides. So when we add a 4 to an 8 to a 4 radical 3, what pieces can we combine?
Okay, well, I'm thinking back to when we did this. We can only combine things that have, like, radicals. Okay, so I only see one radical thing, so I can't combine that technically with that. So I'm just going to add the 4 and the 8 and get 12, and then I'm just going to put plus 4 radical 3. And I know a lot of people want to put 16 radical 3, but it's not the same thing.
Right.
So be careful with that.
Okay, wonderful.
All right, let's find the missing side lengths of this, and this is just strictly finding the missing side lengths. So first things first, is it a special right triangle?
Yes, because we've got the 30 already marked, we've got the 90, so that has to be a 60-degree angle that's not marked.
And which piece or side are they giving us?
They're giving us the longer leg. I wanted the shorter leg.
But we can deal with this.
We can get there.
So if they're giving you the longer leg, let's work backwards. Which one do we have to find first?
Well, everything is in terms of the shorter leg, so I need to find the shorter leg first.
So let's just label maybe that X.
Okay.
All right. So what is the relationship between the shorter leg, this is the shorter leg, and the longer leg?
I know that the shorter leg times radical 3 is going to give us that longer leg.
So this is kind of, in a sense, like with the 45, 45, 90. So if you're given the longer leg, to go to the shorter leg, you're just dividing, okay, because working backwards. So we're going to have to divide each side by radical 3. So you get X equals whatever 14 over radical 3, but we can't leave it like that, so what am I going to do?
Rationalize the denominator, so top and bottom times the radical 3. So 14 radical 3 over 3. And 14 doesn't divide by 3 evenly, so that's just my answer.
So this is
that's the shorter leg.
Okay. So we've got one piece found. We need to find one more side, and the side we're missing is the hypotenuse. And what do we know about the hypotenuse?
The hypotenuse is twice the shorter leg.
So basically, I'm going to do 2 times what?
2 times the 14 radical 3 over 3.
Okay, so how am I going to do this?
Okay, well, I remember multiplying fractions, because I've got a fraction there. I'm just multiplying the numerators and multiplying the denominators, which is really, it's a 2 over 1.
Yeah.
So I'm really just taking 2 times the 14 because it doesn't have a radical to multiply the radicals. So I'm just going to say 28 radical 3 over 3.
And does 3 divide into 28?
No.
Nope.
So that's
this
just my
is
answer.
Your hypotenuse.
That's the hypotenuse. And since here they just said find the missing side lengths,
that's as far as you could go.
Okay.
Or as far as you needed to go.
Right. Okay, next one. Find the area of this equilateral triangle. Let's talk vocabulary for a minute.
Okay, first word I see is area, and I know area of a triangle is 1/2 base times height. And so I'm already looking to see, okay, what do I have? I have the height. That 3 is the height. I got that. I gotta find the base. And when I think about base, I think that it's a side length. And it's the side that the height is perpendicular to. So that piece is what I'm trying to find. But I'm not done when I find that. So I got to then substitute in. But if once I get it, I'm almost there.
Right. So this is our goal. And notice that this is just one of the sides of the large triangle that we have here too. Okay.
Now, another word, you said vocab. The next word I see is equilateral. And I know in an equilateral triangle, all the sides are congruent. But I also know...
I'm kind of mark that. I'm just going to put it in the middle for right now.
That sounds perfect. I also know that all the angles are congruent.
Yeah, because equilateral triangles are also...
equal angular. So let's go with that. If all the angles are equal, so 180 divided by 3 is 60. So all of those angles are 60 degrees. And I'm hoping now something is clicking here, guys.
I'm hoping so too. And notice we've been talking about right triangles this chapter. And obviously if it's equilateral, it's not a right triangle. But what else do you see?
Well, I see that when you draw in that altitude, there is 2 right triangles formed. And we have a right angle, we have a 60-degree angle, and that's a 30-degree angle.
Yeah, so the whole thing together is 60. So really, that altitude is going to bisect
that angle.
Yeah, and they're each going to be 30.
So really, we are dealing with a special right triangle.
Love it.
And the one we're dealing with is a 30, 60, 90 triangle.
I'm going to draw that down here just to make sure we're good.
Now, while she's drawing that, while you're thinking here, think about, okay, they're giving you our goal is to try to find that whole side length. They're giving you, in that special right triangle, the longer leg. And what we're trying to do, well, anytime they give you the longer leg, we got to then find the shorter leg because we can't do anything without the shorter leg. So I'm just going to work backwards. To go from the longer leg to shorter leg, I'm going to take the longer leg, divide it by radical 3.
Okay, so when I rationalize that denominator, that's going to give us a...
3 radical 3 over 3, which simplifies to radical 3.
Wonderful. So that's the shorter leg, was a radical 3. Radical 3. And then what about the hypotenuse?
That's going to be twice that shorter leg, so 2 radical 3.
Now, I'm going to go back to my picture, and I'm going to mark these things in the picture, too.
I like that idea.
So going back here, we said that this was my 30, 60, 90. So this is my 2 radical 3. And this was just my radical 3. Now, notice that this over here would also be what?
Radical 3, because actually those 2 right triangles are congruent to each other.
Congruent, exactly. They had... Really, the angles are all there, but we've got that angle side angle idea we can talk about. We've got a reflexive side. We can talk about lots of different parts. All right. And if I add those together, I do get my 2 radical 3 for my base, right?
Yeah. Well, and it should be because it's equilateral.
Exactly.
If that 2 radical 3 is that hypotenuse, then all the other sides have to be the same.
Exactly. Now, the goal here was to find the area.
Okay.
So I found all the necessary information. We know it's 1/2. The base, which we said was a
2 radical 3
times the height, which we said was 3. All right.
So I'm gonna do the easiest thing I see is take 1/2 of 2. That's 1. So it's gonna be basically 3 radical 3.
Love it. So 3 radical 3 would be my area, and you could have done these in any order. You could have done the 6 radical 3 first and then done half that, as long as you end up with your 3 radical 3.